the tension builds.
Okay, here's hoping. Hello, everybody, and welcome to another edition of this Future in Space Hangout. My name is Tony Darnell from deepastronomy.space, and today we're going to close out our series of updates on the 4 missions being considered for the future of space. Okay, here's hoping. Hello, everybody, and welcome to another edition of this Future in Space Hangout. My name is Tony Darnell from deepastronomy.space, and today we are going to one of those days. We're going to be taking a look at the future of space telescopes. These missions are designed to be the next generation of space telescopes that will be launched sometime in the coming decades. Now, I want to thank our sponsor, the American Astronautical Society, for sponsoring the Future in Space Hangouts. The AAS helps shape the U.S. space program and is recognized for its excellence of its national meetings, symposia, and publications that give members opportunities to meet with leaders in their fields and exchange information and ideas. And I want to let you guys know, on October 23rd, from the 23rd to the 25th, the AAS is holding the Wernher von Braun Memorial Symposium in Huntsville, Alabama. The link to that meeting is in the description box if you want to learn more about it and what they do. So check that out. And I want to thank them again for the sponsorship. Okay, so we've talked about the Origin Space Telescope, which will focus on the question of origins in the universe. We've from life all the way to galaxies. And we've talked about the Lynx Space Telescope, which is a next-generation X-ray telescope designed to provide higher resolution X-ray images of the cosmos that outdoes the Chandra X-ray telescope. And we've talked about HabEx just last time, the habitable exoplanet observatory that will try to directly image planetary systems around sun-like stars. And today, we are rounding out our series with Luvoir, the large UV optical infrared surveyor, which, as its name implies, is a multi-wavelength observatory that will give us a glimpse of the early universe, galaxies and their formation, star and planet formation, and has a major goal of characterizing a wide range of exoplanets, including those that might be habitable. So all of these missions that we've been talking about here on Future in Space are finishing up their proposals to the National Academy of Sciences to be considered in their decadal survey that's coming up in 2020. And I'll let my co-host tell you about that in just a minute. But first, I want to say that we are streaming live on YouTube, Facebook, Twitter, and Twitch, and we are welcoming your comments and questions on all of these platforms. So I hope you'll take advantage of this opportunity to speak to professional astronomers, because you don't get those every day. And I want to welcome everyone also watching this on the VOD, or the video on demand of this stream, or if you're listening to the podcast, if you're listening to that. So if you are listening or watching after the fact, we have a link to a Google Drive folder which has many of our visuals on it, and you can get access to those. Especially if you're listening to the podcast, you might want to look at those later in case you're missing out on all the cool visuals that we're going to show up. So let me bring up my panel here. There we go. Okay, so today we have, well, let me start with my co-host, Dr. Harley Frandsen. Hi, Harley.
Hey, good afternoon. Good afternoon, everybody.
Good afternoon. You want to tell us a little bit about the decadal survey and all of that kind of stuff that's coming up?
Sure. We'll be hearing quite a bit more as we speak with our 2 guests. And again, welcome to the participants, the audience of these Hangouts who've been following us for the last few years, as we have about once a year. We've been bringing to you updates on the 4 major concept studies that you mentioned. Today will be the 4th of the 4 for this year. And then just a note, if you count it, since 1950, the National Academies of Science have carried out so-called decadal surveys, happen once a decade. And the primary purpose is to recommend to the National Science Foundation and to NASA, to Congress, to the White House, what are the priority science goals, possible mission concepts, possible technology areas, other areas of policy for the coming decade. About 3 years ago, I think it was, NASA headquarters began putting money into the 4 concept studies that you already referred to, Tony, and so that they may develop in increasing detail their science goals, possible, feasible, plausible instruments for their missions, and designs for the missions to be carried out that will be, as I said, beginning in a little bit less than a year from now, be evaluated by the national academies. It's expected that the national academies will report their recommendations out, which will be made public about 18 months later. I believe the schedule is still a little bit up in the air. We will be visiting with those 4 missions, the concepts, as that process continues for those folks who are interested in it, because the process will determine eventually the mid-century's priority science program and mission or missions to achieve it. So again, thank you to the AAS, the American Astronautical Society, and back to you, Tony, to introduce our guests.
All right, good. So right next to me in our astronomical Brady Bunch that I have set up here, next to me is Dr. John OMeara. That's right. Here's a story. You got to sing the song too. Oh, you got to. Well, you got to. Yeah, there you go. Okay, that is Dr. John OMeara. He is from St. Michael's University. Welcome, John. Welcome, John. It's good to have you. And right next to Harley is Matt Bolcar. Also, he is also from NASA. Goddard Space Flight Center, same place as Harley. So welcome, guys. Who wants to start by giving us the big overview of what the heck Luvoir is? And while you're describing it, I'm going to show the beauty shot you guys gave.
I think John does.
You want John to do it? Okay, John, go for it. And while you're talking, I've got the beauty shot looping. Are you there?
Oh, John. The floor is yours, John.
We cannot hear you.
How about now?
Now
there you go.
There you go.
Okay.
The joys of live radio.
Phew.
All right. So the singular boring thing about Luvoir is its name. So Luvoir stands for the Large UV Optical Infrared Surveyor, and that's where the boring ends. Luvoir is intended to be, sort of philosophically and engineering-wise, the next successor to the Hubble Space Telescope. It covers the same sort of wavelength range as Hubble, so from the far ultraviolet up to the infrared. And that's also where some of the similarities ends, because while Hubble is about a 2.4 meter telescope, Luvoir is anywhere between 8 meters and 15 meters in size. And we can talk about the 2 different variants that we've been developing for Luvoir. And as Tony said in the beginning, you know, the goals for Luvoir go anywhere between finding the earliest stars and galaxies out there in the universe, to watching stars and planetary systems form, to watching galaxies form and evolve over time, and to getting down to do a proper census and characterization of many tens up to 100 exoplanets out there in the search for life. And the way we like to characterize it is we like to talk about telling the story of life, that Luvoir is really going to try to go after just about every epoch cosmologically, all the way down to the formation of planets around other stars, and looking into their atmosphere, seeing whether or not there are biosignatures around some of them. It's an extremely ambitious telescope. It'll have anywhere between 40 and 1,000 times the power of Hubble, depending on what it's doing. And it's just going to be really a transformative observatory for the entire astronomical community.
Okay, since you brought up Hubble, I'm gonna show the comparison video that you had showing the difference between Hubble and Luvoir in size. This thing is huge. It looks a lot like the James Webb Space Telescope, but it's much bigger, isn't it?
Yes, I mean the similarity with Webb arise largely from how we try to make the mirrors work, how we package them up to try to get them inside of rocket fairings, and the absolute master of figuring that out happens to be with us today in terms of figuring out how to get Luvoir in that fairing. But James Webb is intended as being an infrared telescope. Luvoir has some infrared capabilities, but James Webb really kind of stops down at just about the visible cutoff between visible and infrared, and Luvoir instead is really supposed to go between far ultraviolet and about where James Webb begins.
Yeah, and I just want to point out this video I'm showing you guys is looping with Hubble pointing toward the Earth, something you won't ever see happen, and followed by the Luvoir Space Telescope coming at it like a Empire Star Destroyer.
We should point out that Luvoir also will not be in low Earth orbit where Hubble is.
That's what yes.
There's another falsity with that video there.
Yeah, it's also not going to be pointing at Earth. Well,
that's just Hollywood.
Yes, but it's awesome. And then toward the end of the sequence, you can see the comparative sizes between the two telescopes, and it's really quite substantial. Where will Luvoir end up? L2?
So, yeah, right. So we're planning L2, the Sun-Earth Lagrange point, the second one for the orbit for both Luvoir variants. And I think all 4 missions are planning to have their orbit basically at L2. And the reason for that is, primarily because it's a very stable, quiet orbital environment where we can really try to keep the observatory stable for its observations, which is one of its critical requirements.
Okay. Periodic. Whoa. Where did he go? Oh, did we lose? We lost John. Okay. Well, periodically, my video is going to drop out, but I can get it back. My audio won't go away. But apparently John has disappeared. So I'm not sure. I'm not sure what happened there. But it's also not using my video. My video camera just died, it looks like. Okay, well, at least I've got the one on the laptop, so I'll use that. Okay, so anyway, and while John comes back, Matt, so this is a multi-wavelength observatory, something we haven't seen really since Hubble, am I right? Because Hubble has detectors that start in the UV. In fact, it's the only space telescope right now that has any kind of UV capability all the way out to, well, now it's primarily an IR telescope after the latest servicing mission. Mm-hmm. So, JWST won't have it, right? That's going to be primarily infrared. W first, again, infrared. And then if this gets chosen, now we're back in business, right? What's so great? Why not just keep it on infrared? Because everybody loves it. I mean, we're building 2 space telescopes in a row that emphasize it. Why the extra wavelength range?
Well, this is really a great question for John to answer, unfortunately. But the real reason I think is the ultraviolet. I mean, as you said, aside from Hubble, there is nothing out there right now with the same kind of ultraviolet capability that Hubble has. And anyone reading the headlines recently knows that Hubble is, certainly nearing, I think, the end of its useful lifetime. I mean, hopefully it comes back from the latest failure that they had with the gyroscope, and they expect it to last, certainly into their early 2020s. But beyond that, right now, there's sort of nothing really slated to replace it. Luvoir would be the true Hubble successor. People often call Webb the successor to Hubble, but as you stated, it's a completely different wavelength range, different science case than what Hubble can do. Luvoir really would pick up where Hubble left off and cover the same kind of science that Hubble is capable of doing. Mm-hmm. And I think that's the real drive for trying to push down into the far ultraviolet as we have.
And maybe I can fill in, not as successfully as John could do it, but I'm dredging up my past history as a research astronomer. The wavelength regime that Luvoir will pick up, that Hubble has, the visual and down into the ultraviolet, contains significant and important spectral features of actually a few molecules, but also loads of atoms and ions. Important diagnostic features of key processes and important objects in the throughout the universe. The dominant unless they're highly redshifted, the bulk of the radiation from not all, but most objects, galaxies, and stars comes out in the wavelength range that Luvoir will be covering. So it's got the capabilities to study many of the most important objects, to study and understand in detail many of the most important objects in the cosmos.
Okay. Yeah, while we're on this topic, let me go ahead and get Raj Luthra's question in, because it fits right into the current discussion we have. What similarities and differences will Luvoir have compared to JWST?
So, I mean, as you mentioned earlier, Luvoir looks a lot like James Webb. The overall design of it. In fact, if you want to go to slide 5 in that slide package,
just give me a couple. Keep talking, and I'll let you know when it's up.
Sure. So, I mean, that's basically showing a picture of our 15-meter version, the Luvoir A variant. And you're right, it does look a lot like Webb. We borrowed a lot from the Webb design in terms of how to fold up this telescope to fit it inside of the launch vehicle fairing. So, as people are probably aware, Webb has 2 wings that fold back. The secondary mirror folds back. It's got that sun shield that wraps up around it. And all of that is meant to fit a much larger telescope into a much smaller fairing. We kind of took that to the extreme, and so we're trying to fit a 15-meter telescope into a fairing that's only 8 meters in diameter. And so we borrowed a lot of the design cues. So we also have a primary mirror that folds up into multiple pieces. We have a secondary mirror that folds up in front of the telescope and behind it. We have a large sunshade, much like Webb. It deploys differently than Webb's does, but it's a similar concept in terms of a large blanket that will help protect the payload from stray light and from thermal issues. But aside from how it looks, that's kind of where the similarities with Webb end. We've already talked about the fact that the wavelength range for Luvoir is very different from Webb's. I think the science case for Luvoir is different from Webb's. There are overlaps, so Webb will do some exoplanet science, as will Luvoir, whereas Luvoir is looking much more at the Earth-like exoplanets compared to what Webb will do, and other aspects like that. So it looks like Webb, and then after you get past the looks, it's quite different.
Mm. And you have 2 concepts for Luvoir, yes, Matt?
Right. So Luvoir A is the 15-meter version, which I believe we're showing now.
Mm-hmm.
And I think if you go down to slide 19, that shows Luvoir B, which is our 8-meter version. Also very similar in design, although the biggest difference here that you notice for Luvoir B is that it's an unobscured telescope, an off-axis telescope, and that the secondary mirror doesn't actually block any portion of the primary mirror.
Does that mean, I'm sorry to interrupt, does that mean it can be smaller?
I'm sorry,
the primary mirror, because it's off axis.
So going off axis was a way that we actually help, because it is a smaller mirror, because it's only 8 meters versus a 15 meter. By going off axis, we were actually able to recover some performance, because we were able to we don't have that obscuration anymore. The telescope performs better overall with our coronagraph instrument when it's off axis. So going off axis actually made it perform better, even though it's a smaller telescope.
Yeah, right. I just want to emphasize that, folks, because we've been talking about this a lot lately in our Hangouts. Remember we did the Hangout on DKISS, the solar telescope being built on Maui? That is also off axis, and one of the reasons for that design is to keep the secondary out of the way. As you can see in this mirror, it's about 20 meters away from the primary, but it's not in the path. It's not in the way. Whereas if I go back to, let me go back to 5, you can see in 5, you got all these struts and stuff just banging up right in the way of the primary mirror. Now, let me ask John's back, by the way. So let me ask either you or John, why can't you have this 15 meter or whatever, or is it 18 meters? What's
15.
15, sorry. The 15 meter diameter primary, why can't you have that off axis too? Then you get all the goodies.
In theory, yes. In practice, no. There are other limitations to going off axis that make it difficult the larger the telescope gets, particularly trying to fit it inside the fairing. So one thing you'll notice is that the 15 meter version, you'll notice that secondary mirror is about 18 meters in front of the primary mirror.
Right.
For the 8 meter version, the secondary mirror is actually 20 meters in front of the primary mirror. So even though the primary mirror got a lot smaller, that secondary mirror distance is still about the same distance.
And that just, But that just simply means you've got a longer focal length and narrower field of view, right?
Right. So that's being driven by other constraints in the system. But the point being that if we were to take that 8-meter version and scale it up to a 15-meter version, that secondary mirror would be probably 40 or 50 meters out in front of the telescope.
About half the length of a football field.
Yeah, and that starts to really run into some design problems, stability issues, and things like that. So there is kind of a limit, a practical limit to how large you can make an off-axis system.
Okay.
Which is why it looks why we've broken it up the way we have.
But I'm very intrigued by these off-axis designs now. We're seeing them a lot more, and they're in ground-based and now in space telescopes. Okay, so I just want to, while I have Luvoir A up, I don't. I have Luvoir B, but let me get Luvoir A back up. I'm noticing all these mirror segments. This is looking very JWST-y, and are the mirror segments, do they compare at all to JWST as far as the size? There's certainly more of them.
Yeah, they're roughly the same size. They're actually a little bit smaller than Webb's mirrors. There's 120 of them as opposed to Webb's 18, so big difference there. And ours are glass, whereas Webb's are made out of beryllium. So we have planning to use a glass material, which is a lot more stable, thermally stable at the temperatures that we're planning to operate at.
And because this is a multi-wavelength spectra or telescope, the coatings on these mirrors must be different than JWST.
Yeah, these will be coated in aluminum, which has a very good performance. Really, it's the only coating that has good performance in the far UV.
Oh, good old aluminum. Those are the same kinds of coatings, folks, you get on your telescopes at home. So maybe with some other coatings on anti-reflection coatings on top of it.
Tiny bit different, just a little bit.
There's still aluminum. Aluminum's aluminum. Okay, I want to show this deployment video while we talk a little bit about this as well. This is how. Actually, it's not starting at the beginning for some reason, but I'll let it loop through.
The Luvoir A deployment? I'm sorry?
It looks like the 8-meter is all I have.
Okay. Okay.
The Luvoir A, or the 8-meter. So I guess that's B. But yeah, it looks like this is slightly. What kind of rocket are we talking about here? Do we know yet? Hello?
Sort of.
It's an interesting question. I mean, I think Matt's certainly the expert on how we try to package things into fairings, but this question is a good question that's sort of descriptive of a lot of the things that are happening for all of these large mission concepts, which is that we really have to explore the full parameter space of what we think is available and what we know is available now. So you can consider the type of rockets that we know are available now, something like a Delta IV Heavy or something like that with a somewhat sizable 5-meter fairing. And we've seen, the Falcon Heavy launch, for example, and so we know that we know what those capabilities of sort of current generation rockets are. For things like Luvoir A, on the other hand, that will be dependent on rockets that we anticipate seeing coming forward, like the SLS Block 2, or the BFR, or the Blue Origin's New Glenn. But each one of those has different fairing shapes. Each one of those has different volumes and mass capabilities to bring to L2. And since some of those things aren't really etched in stone yet, we have that's part of what's driving our choices of aperture sizes and capabilities inside the telescope to match what mass and volume we take up inside the fairing to get all the way out there to L2. And so it's a fun question that you ask, because we are learning interesting things about rocket designs as they're just as they're coming out and trying to apply them really quickly. And then Matt has to bang his head against a desk to figure out how to get, that extra inch or two inside the fairing. And that becomes this feedback loop. And at some point, and we've done this very recently, you have to finalize the design. You have to stop and you have to say, all right, this is what we're assuming about the range of rockets available. This is what we could package it in, knowing about those rockets now. And it's an important point to emphasize for any of these large mission concepts. The mission that actually launches will not look like the telescopes we're looking at today. These are mission concepts. Technologies will mature, launch vehicles will mature, all sorts of things will mature. This is just supposed to be a broad brush look at what we think the landscape of the 2030s is going to look like in terms of launch vehicles and technology, and making a concept that fits those. But, James Webb does not look today like what it did at this stage in its development. Same is true for Hubble. Same is true for WFIRST or any of those missions. And so that's a really important point to emphasize when we ask questions about rockets and mirrors and all those things.
I think a nice way to put it, John, that was nicely said and a good thing to remember. Maybe a nice way to put it for the audience is that you all and the other three teams are developing a proof of concept that there is a feasible design that can be plausibly designed, developed, and launched. It may not be the design that NASA in the end chooses, but folks are confident that there is a design that could be launched.
Yeah, and just to build off of that for a second real quick too, that's kind of the reason why we have two designs, right? So the 8 meter and the 15 meter kind of bracket either end of a range of concepts. So you can imagine that whatever launch vehicles do become available, you can kind of figure out that there's going to be something somewhere between 8 and 15 meters that will fit in that fairing. So this is meant to be a proof of concept that you can scale these designs either up or down from either end to find that sweet spot that will fit in the fairing that exists, fit in the launch vehicle that exists, and accomplish the science that has been laid out.
Yeah, good point. So what is you and both Matt and John were hit on this point, so I may be asking you to repeat it. Once again, for the audience, what are the issues that right now, because you're about 7 or 8 months before you have to turn in your report, so what are the issues that are really keeping you awake at night?
So I guess the thing that keeps me awake right now is it's the technology. I mean, that's really the last piece that we have to put together here. Now that we've got a good understanding of the architecture, and we have a good understanding of what technologies are needed to make these architectures, to really enable these architectures, it's mapping out how we're going to develop those technologies, in a suitable time limit. So there's a lot of pieces to this that are critical to making the exoplanet science case achievable. The coronagraph instrument, the level of stability that's required on the telescope. Those are key challenges. And so there's a lot of work going on right now to start laying the bricks for how we're going to achieve those technical challenges. And then figuring out, in the next 2 years, next 3 years, next 5 years, what has to happen to really get there. That's the major piece I think that's left from the technical side is mapping that level of work out and understanding just how long and just how much it's going to take.
Mm-hmm. Yeah. In many cases for these big complex missions, it's somewhat arbitrary to divide a line between the engineers, the technologists, and the scientists. Matt's the engineer and technologist. John, you're the scientist. Are there things that keep you awake at night at this stage in this design?
Oh, I think Matt and his team of amazing folks have it much harder than we do right now on the science side. In many ways, much of the heavy lift that we did on the science front was surveying what we thought the landscape of science in astrophysics and in planetary and in all the things that we might want to do with this telescope, trying to survey what we thought that landscape might be in the 2030s, 40s, 50s, and beyond. But at some point, once we identified what we called signature science programs, and I can go through those at some point if you'd like.
Oh, definitely.
Once we identified the key science metrics, from there we wanted to make sure that we had an observatory that was powerful and flexible enough to do the science that we simply can't think of right now. Right? Hubble today is doing science that was never dreamed of in the 70s when they were starting to set some of the ideas for it. Certainly not in the 1969 paper to the academies on the uses of a large space telescope. And so in many ways, we've set the science tall poles in terms of exoplanets, in terms of cosmology, in terms of the solar system. But those tall poles may not be there in the 2030s, 40s, 50s. And new tall poles will definitely emerge. Our field is very good at that. And we wanted an observatory that's powerful enough to do all that science and more, and to go after the unknown unknowns as they arise.
Mm.
Okay, let me just get a quick question in from Hans Milling because it's related to this particular area of our conversation. JWST is 6.5 meters in diameter. 8 meters doesn't sound that much larger. That's like twice as much light. Will that make a very big difference?
Yes.
Why do an 8 meter one?
Okay, so for a variety of reasons. First and foremost is considering the wavelength space.
Right.
Right now, the largest telescope in space that's doing ultraviolet anything is the Hubble Space Telescope at 2.4 meters. The James Webb Space Telescope will not do any ultraviolet light. It will barely do any visible light. It's an IR machine. And it's designed to do a suite of science that is best done at the infrared wavelengths that JW can do. So the gain in aperture, we shouldn't think about 8 meters versus 6.5 for most of the wavelengths that Luvoir will be looking at. We should be looking at 8 or 15 meters versus 2.4, which is what we have with Hubble today. And there the gains are quite profound. The other is the type of instrumentation that's going on there. The coronagraph in Hubble is rather crude. It's a piece of metal that sticks in front of something. The coronagraph on JWST is a little bit more powerful. The coronagraph intended for WFIRST is really starting to get powerful, but none of them are powerful enough to eclipse completely the light of a sun-like star to go after an Earth-like planet. And to do those kind of things, you need the combination of aperture and instrumentation to be able to go after those objects. And there's plenty of other differences, but it really boils down to the science questions you're asking, the instruments you have to go after them, and also the type of programs you're doing. Are you doing only large key projects, or are you doing a smattering of science anywhere between an hour long and hundreds of hours long, kind of like what we do with Hubble today? Be it, there are programs that are 1 orbit long, there are programs that are hundreds of orbits long. And so the 8 meter is going to be able to do absolutely amazing science, and the 15 meter is going to be able to do absolutely transformative, amazing science beyond that. Like Matt said, we're trying to look at a continuum of options, and that presents a continuum of science. But James Webb will do fantastic things in the infrared that Luvoir wouldn't be able to touch simply because it's going after a different block of wavelengths.
Actually, this is a good point to bring up in case there's some folks in the audience may not know it. John and Matt, actually, you both are heavily involved in this. Describe what a coronagraph is and the level of performance that you all are aiming for Luvoir to achieve its exoplanet science program.
And if you got a slide for me to show, I'll put that up too.
Unfortunately, I don't think I have one in the package.
Oh, okay. All right.
I'll give the simple science introduction, and then I'll let Matt talk about sort of the amazing engineering that has to go into such a thing. The simple science introduction is that if we were to take our solar system, for example, and put it at 10 parsecs away, so say 30 light years away, and you ask yourself, all right, can we see the Earth orbiting around the sun at that distance? And nominally, with the current technology that we have, the answer is no, for 2 reasons. The first is the separation on the sky between the Earth and the sun. Between the Earth and the sun, at 30 light years away, it's about the width of a human hair held at arm's length if your arms are 200 meters long. And so to be able to see the space in between those requires that you have really, really, really good angular resolution, spatial resolution. For that, you need a huge mirror. The other thing that you have, the other problem that you have, is that the Earth, compared to the sun, the reflected light off of the Earth compared to the sun is about 10 billion times fainter. And so it's really, really hard to see the Earth against the glare of the sun. And for that, you need a coronagraph. And a coronagraph basically is an exquisite instrument that tries to block out as much light from the star as it can without blocking the light of anything that's nearby on the sky. And so you have this difficult problem of turning something that is 10 billion times brighter off and still being able to see things very, very close to it. It is an engineering grand challenge for telescope instrumentation. It's been something we've been slowly developing up on both the ground and in space. Ground-based coronagraphs have been around for a while, of various abilities, various contrast ratios. We like to talk about contrast, but it's a very, very difficult thing to build. And I'll let punt to Matt for some of the reasons why.
He's going to build it. He's going to build it for you.
Yeah, and Matt, if you could also put that in context with, we talked about HabEx last time, and they're planning on doing a lot of this blocking with a star shade and also on board Leo stops and things like that. So why don't you go ahead?
Right. So our coronagraph instrument is very similar to the HabEx coronagraph instrument, but like you said, HabEx is also planning to use a star shade which is another way of achieving that 10 to the 10th contrast that John mentioned. So the idea, again, you want to block the starlight, but let the planet light through. And you can do that one of two ways. The star shade is basically, it's equivalent to putting your thumb, in front of the sun. You're literally flying a large disk in front of the telescope to block that starlight, and the disk is just big enough so that the star gets blocked, but the planet light gets by. A chronograph, on the other hand, does all of that inside of the telescope. So what you're doing is you're taking all of the light that has entered the telescope, and now you have to filter it to remove that starlight. And that, as John said, is an extraordinarily challenging problem. One of the reasons one of the reasons it's so challenging is because of a phenomenon called diffraction, which is just it's a fundamental physical limit to the way that optics perform. And so you can place these various optics in place. You can place an occulting mask to block the starlight. You can place a Leo stop to further filter that light out. But ultimately, the optics in your system are not going to be perfect. And so those introduce further errors that are even harder to remove. So now you have to add in deformable mirrors, which are active mirrors that, as their name implies, the shape deforms to correct all of the errors in your optical system. And then once you've done all that and you've actually achieved that 10 to the 10th contrast, now you have to hold it long enough that you can actually collect enough photons from the planet to see it. And so that implies that your system has to be very stable. And the level of stability that's required is on the order of 10 picometers. Pico is another 1,000 times smaller than a nanometer. So 10 picometers.
I think it's a trillionth, isn't it? A trillionth of a meter?
It's sure. It's really small.
Okay, but what do you mean by stability? Nothing can move, nothing can flex.
That's correct. So in the time frame. So yeah, exactly. So we have on board these control systems which will actively control the telescope. And it takes a certain amount of time to estimate the state of the telescope and then issue a command to correct that state. And in that time period, which is on the order of about 10 minutes or so, the telescope cannot change the wavefront area, the optical quality of the system cannot change by more than 10 picometers on average. And so that, a hydrogen atom is, I think, 50 picometers. So, that gives you an idea of how challenging of a problem this really is. And it is as John said, it really is a great engineering challenge this is the kind of problem that engineers love, right? They love to figure out, can I do that? And how can I do it? And what's it going to take? And that's the problem that we're trying to solve.
Okay. And this would help you with one of the science goals of directly imaging exoplanets. Are there other science cases for blocking out starlight? I do want to get to some of the science cases here, but while we're talking about the coronagraphs in particular, I'll ask about that.
There are a number of interesting things. I mean, there's not just planets, but protoplanetary systems. As you're trying to look at the disk of material that eventually coalesces into stars, being able to block out the central starlight there is somewhat helpful. There are interesting people have looked at ways of looking at active galactic nuclei, so supermassive black holes accreting things and getting very bright, trying to look deep down very close next to the supermassive black hole and see the disks of materials falling in on that. You could potentially use a chronograph for that, but its primary purpose is really to go after exoplanet systems of various flavors, not just Earth-like planets around sun-like stars, but the whole spectrum of exoplanets out there, going after the whole diversity of exoplanets, because if we're going to try to understand how life emerges in the universe, you really need to understand all the possible environments that it could be emerging from.
Okay, so basically anywhere where you have to block out a very bright thing that is next to a very dim thing that you want to see, whatever the case may be, that's where you're going to be able to use these coronagraphs.
That's correct.
All right, let's talk a little bit about the science. And the way I want to ask you this question, I want to know, what are you most excited about being able to do with this telescope that nothing else is going to be able to get you to do? What is the biggest science, most exciting science you're hoping to get out of it, John?
Well, do I have to only pick one?
No, you can pick three.
All right, I'm going to give you three. One, we will be able to characterize the atmospheres of many tens of planets around other stars. By characterize, I mean we will get their spectrum and look for biosignatures. And even if we don't find the biosignatures, we will actually be able to measure the atmospheric properties of planets around other stars, rocky planets around other stars, and that's absolutely transformative. It may be that we actually detect biosignatures and the markers of life around planets around other stars, and that's just phenomenal to me. That's not what I do for a living, so I'm going to punt to number 2. Number 2 is for galaxies and how they change with time. We will be able to look at galaxies in such exquisite detail that, I don't know if you're familiar with gravitational lensing, that these beautiful images that the Hubble Space Telescope gives of gravitationally lensed galaxies, and
yes,
you can actually
talked about
see
that many times.
Well, every single galaxy that Luvoir would look at would look like a gravitationally lensed galaxy with Hubble today. That is to say, we can look deep, deep, deep down inside these galaxies in very, very high detail. The figure of merit, if you know what a parsec is, the figure of merit is that we will be able to see objects the size of 60 parsecs or larger anywhere in the universe within galaxies with Luvoir, which is utterly transformative. We will see the assembly of galaxies. We will see how they change with time. We will be able to image individual star clusters in galaxies 10 billion years in the past. It's really going to be fundamentally transformative.
Wow. Well, in that case, if you're looking at nearby galaxies, let's say Andromeda, could you resolve individual stars in that?
Oh, absolutely. We could resolve certain individual stars all the way out to Coma cluster with something like Luvoir. So not just Andromeda, but our nearby galactic neighborhood, we will be able to do census of individual stars down to G-type stars like our sun. For Andromeda, we'll be able to go down to very, very, very low luminosity stars. Okay. So it's going to be quite transformative.
Okay.
And then number 3.
Okay, go ahead, do number 3.
Number 3 is we will finally get to understand how galaxies get their fuel, transform it into stars, and turn that back out into the universe in the form of the gas, not just the stars themselves. So the ultraviolet capabilities of Luvoir will be able to actually get exquisite 2-dimensional and 3-dimensional maps of the gas surrounding galaxies, watching the gas flow into them, turn into stars, come back out. And we'll get to see the transition between galaxies that are like our own, forming stars today, to galaxies that are ellipticals that are red and dead, and trying to understand that process has been something that's been quite a challenge. And I'm so excited to be able to see Luvoir take data of the quality, if not much more superior than the best cosmological simulations are doing today to try to simulate that process. We'll be going back into the era where the observations themselves are really better than and are driving the next generation of simulations.
Okay, let me put a little bit of what John said in context, if I did the math right. John, did you say, I did not know this, it's an interesting figure of merit, did you say that Luvoir will, the Luvoir version, would be able to resolve about 60 parsecs anywhere in the cosmos? Anywhere in the universe, because of the way the expansion of the universe. Right. Yeah, no, that works. Yep. So for the audience, what that means is that, and this is just in round numbers, that you could put around 1 million pixels across any galaxy. No, 1 million pixels on, not just across, 1 million pixels image of a galaxy anywhere in the universe. I just did, typical big galaxies, 100 parsecs across. If you can resolve 60 parsecs, that's, in round numbers, that's 1,000 of those things across the size of a galaxy, 1,000 times 1,000, around a 1 million pixels, give or take. And Harley, I think the other way to put it is that same spatial resolution would allow us to image something about the size of Texas on Jupiter, and be able to. Yeah, but who would want to? Plenty of Texans. Mainly, man, no, I was dissing some Texans.
Yes, you were.
Well, I mean, Luvoir is also going to be amazing for solar system science. The images we take of Jupiter with Juno today at Perigove. So when Juno is right up next to Jupiter, Luvoir will be able to take that quality image of Jupiter at any time.
That'll be
very cool.
Okay, well, let me ask about the sensitivity then. I get that you can, let's say out to the Coma, in our local group, the Coma cluster, we can resolve individual stars. Could the sensitivity of the detectors be such that, and I know I'm stretching it here, but is it possible to be able to detect dips in brightness? In other words, transiting exoplanets.
So we did a fun back of the envelope calculation that, if you demand 1% accuracy, so typical transit accuracy of maybe 1% starlight dip, we could do transiting exoplanets in the Large Magellanic Cloud. Just fine.
The nearest big irregular galaxy.
Yeah, the nearest big irregular galaxy. For really, really bright stars that we would be able to resolve individually, probably not. And that's probably also okay, because most of those stars, if they're harboring planets, those planets are having a really bad day. But another way of thinking about the sensitivity, Tony, is that one of the most iconic images ever taken is the Hubble Ultra Deep Field, right? It's Hubble pointing at the sky for 1 million seconds, and it goes down, to it's one of the deepest images ever taken with a telescope. Luvoir does that image in 47 minutes.
Because of its diameter, primary mirror size, and the sensitivity of
because of its primary mirror size, because of its sensitivity, but it's also doing that image in 47 minutes at the resolution where we're seeing exquisite detail in those galaxies. So the value add is not just the depth, the short integration time, it's the immense spatial resolution. It's the ability to look deep down into those galaxies, see star clusters in them, and all those kind of things. It's going to fundamentally change how we look at galaxies and galaxy evolution. And we do not currently have a cosmological simulation that can go down to the depths that Luvoir would be able to do observationally.
Okay. Wow. Well, because this is a Future in Space hangout that's sponsored by the Astronautical Society, I want to go back a little bit to the engineering aspect of this telescope, because that's sort of our emphasis here. But I got to ask you, Matt, when you guys are currently, all of you as a team, are working on your proposal that's due next year, and then it will be considered by the National Academy of Sciences. Do you guys have a review process yet, or are you just working as a team to figure out how are we going to get the science cases satisfied, from an engineering perspective, and you're not worrying about anything else beyond things like schedules or anything like that yet? Are you just trying to figure out the basics of the equipment that you're going to need to get this done at this stage?
A little bit. I mean, we work very closely with the STD team, so we should probably talk a little bit about the structure here. John is a member of the Science and Technology Definition team, so there's 25 members to that team that are made up of professors like himself, a couple other people from other NASA centers, but largely it's drawn from the academic community to prioritize the science cases that John has described. Then, aside from that, there's the engineering team here at Goddard. So basically, we work with the STDT. They come to us and say, here's the science we'd like to perform, and then our job is to go and design that mission that will achieve that science. And so there is a lot of iteration with the team. Every now and then, John will come to us, or one of his colleagues will come to us and say, we want to do this. And I'll say, sorry, John, that's just not possible. They say, no, but really, we really want to do it. And then I go figure out how to do it. So there is a lot of iteration like that between the STDT and the engineering team. So we are making sure that the designs that we're developing actually can achieve the science case that John has laid out.
But there's no actual review process yet. You don't have to, like with the National Science Foundation or NASA, you like get a review of your mission like JWST has to go through. Well, so it's not there's no formal you're probably thinking of things like a preliminary design review or critical design review. That's right. Yeah. So we are not in that phase yet. There are more informal reviews that we have to go through. So at Goddard here, we will hold what's called a red team review of the proposal. So once the proposal is written, we'll give it to a number of people who are not part of the Luvoir team, who will critically read it and say, like, does this make sense? Does it hold together? Separate from that, we'll be submitting a portion of the work to headquarters, and they will do another independent review, completely separate from Goddard at the headquarters level. And then, of course, the ultimate review is really the one that the National Academies will do. So they will take our report, they will review the science case, they will review the engineering work of it, and they will say, does this look like a compelling mission that is both feasible and executable, within the next couple decades.
So if things go well, I mean, this is very optimistic. When might we expect first light from Luvoir?
probably looking at somewhere in the mid to late 2030s, I'll say.
Yeah. Yeah, that's what
I mean, Harley, a lot of that question depends on things that the SDDT simply doesn't control.
Yeah.
It depends on how aggressively Congress would want to fund such a program. It depends on how aggressively technologies can mature. You know, one of the things that we're doing now, and all 4 of the mission concept teams is doing now, is doing a much better job, a really robust job at looking at the technologies, the risks associated with those technologies, and critically, the path to lowering the risk of those technologies. Like, what do we have to do in the next 5, 10, 15 years to retire much of the technological risk so that when we get the green light to start building, that it is going to be a much smoother process to get towards completion. And so a lot of the things that could affect a first light date for Luvoir in many ways don't have to do with Luvoir. They have to do with the steps building up to Luvoir. So a good example for that is WFIRST. WFIRST has this coronagraph instrument on it, and that is in many ways a technological test bed for some of the critical technologies that would go into a Luvoir coronagraph. James Webb is a great technological test bed for deploying large aperture segmented telescopes in space. And so a lot of these things are steps up, but first light has a lot of things wrapped into it that we simply don't control.
Yeah, and that I got to say, these deploying telescopes are starting to give me nightmares when I think about what's got to happen. So I want to have one more question for Matt. Then I got some questions to read out from the chat. Matt, you know about you. I'm sure you're watching JWST with intense interest. We all are.
Mm-hmm.
What's your biggest concern technologically or from an engineering perspective? What is it you are most concerned about with respect to Luvoir and getting it built and deployed?
I think it really comes down to that stability question that I mentioned earlier. The 10 picometer stability number is something that is unprecedented in terms of the challenge. And as John said, we're trying to be very, careful about laying out that technology plan, that technology story, about how all the pieces are going to work together to achieve that level of stability.
Well, because that affects the entire structure, doesn't it? Every hinge, every bolt, everything that works together cannot flex or stretch or break or wobble or do anything to within this picometer level amount.
Yeah, and the team that we have here is phenomenal, but it is a small team, and designing the system down to the level where we're going to be, where we can point to it and confidently say, yes, this is going to achieve the 10 picometers is a challenge. And so we are laying out what we think it will take to do that, but it is going to take the next 3, 5, 8, 10 years to develop those technologies and really show beyond a shadow of a doubt that is all achievable. I mean, we are putting together that plan right now. And I mean, let me be clear. I fully think it is achievable with the technologies, that are in the pipeline.
Okay. But Matt,
it takes that level of work.
You're not being guilty of this excessive optimism that we hear about in NASA. you have good reasons for thinking that, right?
Yes, I have good reasons for believing that it is achievable. But yeah, I am also I'm an engineer. I'm not afraid of saying, it is extraordinarily challenging. It's going to be very difficult, but I think it's possible.
It's important. It's also important to stress that there are industrial partners that are working with us right now that are looking at many of these things right now. So, our optimism is grounded in many ways in emergent technological advances that are being made by partners in industry and some of the wizards at Goddard and JPL. These things they're not sprinkling magic fairy dust on mirrors and hoping that it works. There is active development in many of these issues that's going on right now and is showing immense promise.
Just as a quick example, about 20 yards down the hall from me, there's a lab where they have an interferometer set up and they are measuring single-digit picometer displacements of an actuator. So we have the capability. We can measure picometers. We can move things at the picometer level. And we can verify that, yes, in fact, it did move as far as we think it did. So those are the building blocks of being able to say, we think we can build a structure that is stable at the picometer level, or we think we can control this mirror's position to within a picometer.
Okay, well, let me get to some comments here. Dan Edwards is commenting, quote, anywhere in the universe, this is going back to what John said, by which he means a relatively small redshift. I don't think that's what you meant, did you?
I mean,
anywhere in the universe means everywhere.
I mean, anywhere in the universe that Luvoir could see. So if we want to look at a galaxy at redshift 9, we will be able to see 60 parsecs or bigger at redshift 9.
Okay.
Redshift 9 is something like, so I'm doing this in my head, John.
You're in a math mood today, aren't you, Harley?
Yeah, it's only like a few 100 million years after the Big Bang.
It's about 600 million years after the Bang.
Yeah.
Oh, it's pretty far, pretty early on.
Anywhere there are galaxies, these guys will be able to resolve 60 parsecs.
And that's one of the exciting things is we're going to see galaxies be born in effect.
Okay, but to be fair, JWST is going to do some of this. JWST is going to be able to look at atmospheres of other planets, first of all, to see if there is one, if it has an atmosphere, and second of all, to get some idea of what's in it. So we've already got that capability, albeit nowhere near at the resolution and the signal level that Luvoir will give us. So we can do that. It's also going to look at the very first stars and galaxies to ever shine in the universe.
Yeah.
So the value here that Luvoir is giving is that we can see these things in much greater detail. The observations are much higher quality and lower error bars than anything JWST could do, not to mention the wavelength capabilities that are coming with Luvoir, right?
And the depth, and also as far as the planets go, JWST will be able to only look at a certain class of planets for their atmospheres. Mm-hmm. Those are typically giant gas planets, as opposed to the atmospheres of rocky planets around sun-like stars. Those are very different types of planets.
Oh, I thought that would be able to do Earth-sized ones too. Okay, all right, good. Well, that's even better. Okay, so Launchpad Astronomy, that's Christian. Hi, Christian. It's good to see you. Will you be able to get some images of supermassive black holes like they're doing with the Event Horizon Telescope? I know they're using an interferometer, but what about imaging event horizons?
Well, we'll be able to get down pretty close. Of course, the hole itself, we're not going to be able to see much of anything, but for holes which are actively eating, I think we'll be able to see some very interesting things down, especially for nearby galaxies with big black holes in them. And I'm really excited to see what Luvoir, for example, could do at the galactic center, or the galactic center of say, Andromeda or any of those nearby galaxies. The problem there is that that's the reason why you go to the infrared or to other wavelengths, is because there's so much stuff in the way that, you have to get through the dust and all that stuff. But for nearby galaxies, supermassive black holes, we could get down pretty close.
Elliot Lawton on Facebook is commenting, why does everybody say 10 to the 10 and not just giving it's just not giving the full picture? I hear you, man. I get that, but that's the only way to really describe in a concise way the size we're talking about. These numbers are not easy to picture. In fact, 10 to the 10 is a ridiculous number to try to actually visualize. I've said that many times, but unfortunately, that's the scales we're talking about.
Well, these 200-meter long arms is pretty tough to visualize. I'm still working on those.
Kevin Lewis, it's good to see you. By the way, Tony, your new brand icon show logos are wonderful. Haven't seen them yet. Yes, there's also one for ExoLife Hangouts, Kevin, just so you know. So if we bring those back. Nick Hardy is asking, is it possible to use a filter in a telescope that will filter all light except the light going through a planet's atmosphere? That's an interesting question. I don't think I mean, that essentially a chronograph is a filter. It's not a filter in the sense of how it's probably being thought of there. I mean, but my gut reaction is going to be no, because the light that you see from the planet is really the starlight, right? It's reflected starlight that you're looking at that has now been filtered by the planet's atmosphere. And so if you were to design a filter to filter out the starlight, chances are you're blocking the planet light as well. Hey, Harley, did you know Alberto's in the chat? Alberto says, but folks working on, you should be here, Alberto. But folks working on LISA are also working on picometer stability for several hours. So Luvoir is not alone. That's a good point. So ESA is, I believe, if I'm not mistaken, is heading the effort to build the laser interferometer space antenna for detecting gravitational waves. Does that also need that same level of stability?
Yes, so they have very similar stability requirements. They are also playing in the picometer regime. The scale is a little bit different. So their telescope, I don't know the diameter of the telescopes that they use to send and receive the laser beams between the spacecraft. so they are looking at picometer requirements over similar time scales, but over much smaller spatial scales than we are. There are 15-meter structure. We're talking about picometers across that 15-meter structure.
Okay, Simon Farmer is asking a question that I think could be good to end with. If NASA tomorrow said new telescopes could only have one new technology, which would you choose?
Oh.
Of the new technologies coming on board.
I was going to say, John, you go first, because, I don't know. It's hard because in the case of Luvoir, to do the exoplanet science, it's not one technology that enables that. It's 4 or 5 or
right. You
6.
got the stability, you've got the mirror size, you've got the.
So if I were to pick one of those, I still don't get the science that I want to achieve. And so basically, what you're saying, the question is really asking, pick one science case that you want to enable. And
well, let's change the question to that then. If you could only pick one science case, what would it be of all the things that it can do?
John's got to answer that one.
Okay, John, go for it. NASA says you can do it. We're going to build Luvoir for you, but you can only look at one thing with it. Why it would say that, I don't know. But, what would it be?
Boy, so I could tell you what I want to do with Luvoir, but I don't know if that's necessarily the answer of what I would pick as the one thing that Luvoir could do. The question of whether or not life is abundant in the universe is a question that transcends astrophysics, and it's a question that transcends just about any aspect of science. It's truly a question that humanity at some point is going to want to answer. So as much as I really want to have far ultraviolet 3D mapping of gas flowing into galaxies, which is what I would do for a living, I think being able to answer the question of whether or not life is occurring only in unique environments like the Earth, or whether or not life is abundant throughout the universe, in other words, being able to do a large census of exoplanets to go after that question, that is the one thing that I would choose for the observatory, because its impact on who we are as a species and how we think about our place in the universe would be utterly profound, and we would emerge a different. Humanity would emerge different, knowing what their context was, and this would be the machine that would help give us that context. So for that reason, I think it's the larger scientific enterprise. If I only get to pick one, but fortunately, we're designing an observatory where we don't have to make that choice.
I know, and that's never the case. These space telescopes end up getting used for all kinds of. Nobody saw Kepler, for example, looking at stars along the ecliptic plane and measuring protoplanetary disk, things like that. I mean, clearly these telescopes can take us to places we can't even imagine right now. So, I don't know, Harley. We've gone through all 4 missions. Do you have a favorite?
I do not.
I don't either. I guess of all of the missions we've talked, I want them all to be built, but I guess the one that seemed the most specific was Lynx, the X-ray telescope. I kind of think all these other ones have a much more comprehensive design to them. But yeah, any one would be awesome. Any one.
Yeah, they're all terrific, and these teams have been outstanding in pulling together their designs, their technology investment strategies, and of course their science goals. Each one of the 4.
So Harley, what can we expect next? What's next from NASA, or from the Academy? I guess I should say.
Well, we heard it. So again, John and Matt, correct me if I'm wrong. You all, according to the current schedule, things can change. They'll be turning in the other 3 teams will be turning in your report around the middle of next year, and it usually takes the decadal surveys about 18 months. This one might be accelerated a bit. 18 months to go through their analysis, the debate, the reviews of their final report, and the big report will land on NASA's and the National Science Foundation's desk. So that would make it something like the end of 2020, early 2021.
Good, yeah. And I hope that whoever comes ahead would be, whatever gets chosen would do a hangout with us and talk about what the next steps are, and so we can keep. This is exciting times, and I can't wait to see what happens. So I want to thank you guys so much. I'm going to have to cut it off here, folks, because we're out of time. My guest today were Dr. John OMeara. He's from the St. Michael's University. Also with me was Matt Bolcar from NASA's Goddard Space Flight Center. He's working on the engineering aspect of the team, and John is working on the science use cases for Luvoir, a next generation large UV optical infrared explorer that will hopefully show us things about the universe we've couldn't even imagine. So I want to thank you guys for spending time with us. Next week I am back with 2 Hangouts. Telescope Talk Pro is back. We're talking about with members of the ELT with Christian Reddy. They're going to be on talking about that. And then the Astro Coffee Hangout with Carol Christian. It's just going to be the 2 of us, I think. I convinced Carol to just chat about Hubble, because a lot has been happening and she is working on the mission. And I said, I think people would love to be able to ask you some questions about Hubble. So it's just going to be the 2 of us talking about the gyros, talking about the future of Hubble, how it's doing, and will it be able to, I want to know if it's still on track to be going at the same time as the James Webb Space Telescope. So we hope that you will tune in for that next week. And until then, thank you all so much for watching. And as always, keep looking up. Yes. These by the way, remember when we got to get Alberto Conti on here to talk about Lisa as well, because he's got apparently a lot of stuff to talk about with gravitational waves. These are our gravitational waves rubber duckies, by the way, guys. Okay, that is it.